So today we're going to talk about the thermodynamics of redox reactions. The idea of how are the quantities of delta G, the free energy, or K, the equilibrium constant, related to the standard reduction potential, E, of a redox reaction. So let's just consider a galvanic cell that involves the oxidation of magnesium and the reduction of silver. So magnesium plus 2Ag, 2 plus, arrow, Mg2 plus 2 silver atoms. So this is a redox reaction where we have the oxidation of magnesium going from a charge of 0 to a charge of plus 2. So it's losing 2 electrons. And we have the reduction of silver going from a positive 2 charge to a net 0 charge. We learned so far that we can calculate the standard reduction potential of the cell by knowing the standard reduction potentials of the two half reactions and plugging them into this equation. So when we look up the values for E naught of the reduction and E naught of the oxidation half cell reactions from a standard data table, we would find the numbers to be 0.80 for the reduction half reaction and negative 2.37 for the oxidation half reaction, which gives us a voltage of 3.17 for this reaction. Again, these numbers here come from a data table. Since this voltage is a positive number, E naught of the cell is greater than 0, we would say the forward reaction is favored. This galvanic cell would generate a flow of electrons that we could harness and measure an electric potential of a positive value that we could use in some sort of battery. But how is this related to delta G or to K, the equilibrium constant? Because again, what's special about electrochemistry is we are intertwining the relationship between electrical energy and chemical energy. How can they be related to each other? So before we start deriving any equations or mathematical concepts, let's first talk about the units. So, units, when we talk about energy, are in joules. And 1 joule is actually equal to 1 coulomb times 1 volt, where C is a coulomb, a unit of electrical energy, and a volt is electrical potential. This is representative of the energy of an electron in joules, but just of a single electron. But in chemistry, we're usually dealing with molar quantities, moles of electrons, not single 2 or 3 electrons. So Michael Faraday developed the Faraday constant, 1F, where this is the Faraday constant, which is equal to 9.647 times 10 to the 4th coulombs per mole of electrons. So this value, 9.647 times 10 to the 4th, represents the electrical charge in coulombs for a mole of electrons. Basically, the way it's derived is just taking the charge of 1 coulomb and multiplying it by Avogadro's number, because we're talking about a mole of electrons. So now how can we use this value to relate K and delta G, our free energy, to E naught of the cell? Well, the relationship that we need to know is that delta G, the free energy available, which remember, delta G is the free energy available to do work of any type. In this case, we're talking about electrical energy, is going to be equal to negative NF E naught cell. So this is one relationship that you need to know. The values, again, delta G, this is our free energy, the energy available to do work, which we can calculate get from a table or calculate thermodynamically. N represents the moles of electrons. how many electrons are getting transferred per reaction. So if 2 electrons are getting transferred, like in the original equation from today, N would be equal to 2. F is equal to the Faraday's constant, which you wrote down above, 9.647 times 10 to the fourth. And E naught cell is going to be the standard electric potential from, standard reduction potential, which we can calculate for the cell if we know the standard reduction potentials for the half cell reactions. Well, we also know, so this is one equation that we need to walk away with. We'll practice in class how to plug in certain values to solve for the relationship between E naught cell and delta G. But what you can clearly see right away is, imagine, we know that when delta G is negative, a reaction is thermodynamically favored in the forward reaction. So just think about it. If this value is less than 0, and we have a negative on this side of the equal sign, these values are going to be positive. So in order for delta G naught to be negative, E naught has to be positive based on this relationship. So when E naught is greater than 0, and when delta G is less than 0, that means we are favoring the forward reaction. We can also make a relationship between K and delta G and E naught. Since we know that from before, we know that the free energy of a reaction is equal to negative RT ln K at equilibrium. By doing some substitution and plugging this equation back into the one up above, we can generate an equation that looks like this, where E naught of the cell is equal to RT, again where R is the ideal, the gas constant, 8.314 joules per mole Kelvin, and O divided by Faraday's constant times the number of moles of electrons times the natural log of K. Again, this equation is just derived by plugging in this guy to the one up above. I'm not going to go through the algebra. Now, since all of these are constants, we can write a value for these three constants at standard conditions. And if we do that, we're left with an equation that looks like this, where E naught of the cell is equal to 0.0257 volts divided by N, again the moles of electrons, times the natural log of K, the equilibrium constant. Okay. So this is the third equation you need to be able to walk away with, again, derived from the guy up above, where these values, since they're constants, are just plugged in. Now we can relate delta G, the free energy, K, the equilibrium constant, and the standard reduction potential of a cell all together to predict whether or not a redox reaction would be thermodynamically favored.